Hello, and a very warm welcome to this, the second in a series of my personal reflections on the connections between polarization in optics and radar. The other, by the way, Poincaré's radar, is also available on YouTube. My name is Shane Cloud, and I had the privilege to work in both areas during my career, that is, radar and optics, and one idea kept coming up in both domains. Dominating problems, constraining solutions, and that is the idea of symmetry. Here, I want to explore these ideas to make a point. I believe that currently the models we use to interpret data, especially in radar studies, are not making full use of the available information. They could and should do better for improved information extraction in remote sensing. But let's not get ahead of ourselves. Let's start at the beginning. Here, I propose the idea that symmetry, usually associated with beauty and harmony, acts in remote sensing to destroy information and even, as we shall see, generate noise. In my view, posing one of the ultimate limitations on our ability to remotely sense the environment. As in the classic poem by William Blake, we should perhaps see symmetry as a double-edged sword, on the one hand useful for constructing tractable models, but on the other a destructive force. Let me illustrate. Symmetry is a simple idea with important consequences, defined as ways to operate on a system without changing. Think of a circle. We can rotate it around and it still remains a circle, an operation leaving things unchanged. And here I will suggest we should get used to the idea of symmetry as an information destroyer. Think again of the circle. Instead of having to give every point around the circumference, just a single point, the center, and a radius will do. These we can consider free parameters that somehow survive the symmetry, and that again we will see is important. It's convenient if drawing circles is your objective, but something of a drawback when remote sensing is your game. And a further problem. Not only will symmetry remove or destroy degrees of freedom, it will lead to disruptive noise on our desired signal. So let's go hear what kind of noise symmetry makes. Well, to find out, we first meet two characters. One whose work first gave us the machinery for describing information loss due to symmetry in multidimensional systems, and another who gave us hope of extracting some residual surviving information. So, first, the bringer of symmetry, famous Norwegian mathematician Sophus Lie, who developed a set of techniques, now called Lie algebras and groups, that show us the menu, so to speak, digs away inside multidimensional systems described by matrices to expose simple key parameters, and show how symmetry, based on the simple idea that 1 minus 1 equals 0, means that we can lose stuff in the mix. Take this beautiful tiling, for example. We can see the individual birds, but if we consider it as an ensemble, we see that the same bird appears in different positions, maybe plus bird and minus bird. And so if we add them all up, they might well cancel. We start to lose detail. Now, I have sat in many a talk listening to people develop elaborate theories. Here, a bit like describing the detailed shape of one of these birds, and they forget that we only ever see a flock of birds, an ensemble, and lots of their proposed model details will be lost in the mix. So it's as well to be prepared for the loss in advance. Symmetry therapy, if you like. So the first key idea is that adding up things with symmetry variation leads to information loss. But how much? With the symmetry of particles amassed in a very large numbers and in a cloud, for example, surely all information disappears. Well, one man showed us that that is not the case, and we go to meet him now. So meet famous Indian astronomer Chandrasekhar. He was the first to show that when you throw a bunch of non-spherical particles into an atmosphere, for example, some structure survives in the scattered light, and the symmetry leads to a kind of noise background. This was the start of what is now called decomposition theory, ways to isolate signals from noise in matrix measurements of scattered light and microwaves. So let's turn to an example. Let's demonstrate first how symmetry leads directly to information loss. So Here is our first example of symmetry destroying information via what is called the reciprocity theorem. Now, this theorem itself relates two problems shown here left and right. The reference one is shown on the left. An incident wave is scattered by some general object, and we observe the light scattered in a direction B. This generates a plane here, which the half angle here, the bisectrix, defines the scattering plane. Now, this scattering problem can be as complex as we like, and it has a scattering matrix, a way of getting the light changed from X and Y polarization input to X and Y polarization output. And that can be represented by four complex numbers, A, B, C, D, as shown here. Now we consider another problem over here. And in this problem, as all we do, it's the same scatterer. We just switch the transmit and receiver. So instead of having light coming in from A, we have the light coming in from B, and we observe in the direction A. Now, you might think that that's going to be a completely different problem, but it's in fact related by the reciprocity theorem. This means that we don't need to recalculate the scattering matrix for this problem. We can get it from the original. Now, there's a few coordinate flips. You can see there's a few y's and sort of change direction here. And those minus signs mean that the scattering matrix for this reciprocal problem is not A, B, C, D, but A and D are the same. But these off-diagonal elements, these are the cross-polar elements, the ones that if you put light in at X, it comes out as Y, and vice versa. They are flipped over. So we've got a transpose here, the B has gone here, and the C has gone up there, and we've got a negative sign here. So this saves us calculation. That's good, and the reciprocity theorem is widely used to help solve these problems, which are the reciprocal of each other. But there's a slightly dangerous thing going on here, and that dangerous thing occurs when we consider backscatter. So that is, we take B and we move it around here to A, so that the transmit and receiver is at the same position. And now we still have a reciprocity theorem, of course, but it means that this matrix now must equal this one. There's a symmetry in the problem. If we apply the reciprocity theorem, nothing changes. It's a kind of symmetry. So this must equal this. And if that's going to be the case, it means that these off-diagonal elements must be related to each other. In fact, they're equal in amplitude, and there's a minus sign here. So we've got AB minus BD. This must be the form of the backscatter matrix. So you can see the consequence of the symmetry is that we've lost a whole channel, in this case C. We've lost information. And we can make that more explicit by defining what's called the Pauli vector. The Pauli vector is just an expansion of this using the Pauli matrices, and comes down to sums and differences of the elements. So A plus D, A minus D, they're all changed. But the sum of the off-diagonal elements, which is B plus C normally, here goes to 0. So this is our first example where we've lost information. And we end up with the difference of them being 2B down here. So what should be a 4-dimensional complex vector turns out to be 3 dimensions just because of the reciprocity theorem. And very often this 0 is left out and we just shorten it down to a 3-dimensional vector. And in radar, which is dominated by backscatter, this is the dominant form. And from this vector, we can then form something called the coherency matrix, which we get by using a product of K times K conjugate transpose to make a 3x3 matrix. And we're going to come back to this matrix T later on, but its form is derived from the reciprocity theorem. So in backscatter, the theorem removes a whole channel of information, HV plus VH in this case. But what about general scattering? What happens if now we open up this problem so that A and B are no longer in the same position? Surely perhaps there's no information loss. Well, there certainly is information loss in the general scattering case as well, and that's what we're going to describe next. But first, let's take a little sideline, because we've seen here this scattering matrix is the basic thing for describing the scattering of light by scatters, but it's not the only way to describe it. We've already seen there's a vector here, K, and there's a matrix T here, which comes from that. All of these are functions of A, B, C, and D. Well, let's try and tidy all that up by showing the scattering triangle. It's a way of representing all the different ways of representing this light problem. So here's the scattering triangle. So S sits at the top. This is our 4 complex numbers. And as we have seen, we can go down this side here to represent the same problem by T, this matrix which comes from the product of the Pauli vector times its conjugate transpose. There is also another familiar way, of course, which is the Muller matrix. And the Muller matrix can be derived from the scattering matrix. And this defines how, this is a 4 by 4 real matrix, defines how the Stokes vectors of the light get transformed by the object itself. S goes to M and S goes to T, but actually that there is an intimate relationship between T and M, and we're going to use that today. If you know an M, you can go straight to T. If you know a T, you can go straight to M using some simple transformations. Interestingly enough, if you want to go back down this triangle, if you have an M and you want it to go back to an S, that's not always possible. Only a subset of Muller matrices, these are called Muller-Jones matrices, because this is called a Jones matrix in the optics community. Similarly, if you want to go from T and you want to go back to an S, we'll see that only a certain subset of them, rank 1 coherency matrices, can allow us to go back that way. But we don't care about this so much. What we care about today is the relationship between these two. So let's revisit reciprocity again. So here it is in the S matrix form. Remember, if the master problem has this as a matrix, then the reciprocal one is related by transpose and minus signs. So let's put these matrices into their different forms. Let's go down this triangle here to M and T. Let's go to M first. So here's the Muller matrix for the reference problem. It's a general 16 real elements, 4 by 4 real matrix. Its reciprocal one, well, take a look at the detail. The diagonal elements again are still the same, but the off-diagonal elements have been flipped in sign and also been transposed. So you can see that 2, 3, for example, has been flipped down here and 3, 2 has gone up to there. So we've had a transpose and a negation. Some of them, not all of them. It's a real mess, just this simple reciprocal operation. Well, now, instead of going from S down to M, let's go from S down to T. And here's what you get with a T. You get a 4 by 4 Hermitian matrix. So it's got real elements on its diagonal and complex conjugates on the off diagonal, and it's generally full. Of course, it's a general scattering matrix. But the reciprocal one looks like this. Now again, the diagonal elements are unchanged, and you can see there's minus signs in this column here and this row, but because of the symmetry of this matrix, there's no transpose. So this is still the 2, 3. It's still the same element. It's just got a minus sign. So whatever this complex number was here, we just get its negative here for the reciprocal problem. Now this may seem like a little small detail, but it's an important detail, as we'll see, because when we put together a cloud of particles, we'll see that reciprocity pops out nice and simply in the T form and not so much in the M form. So we're going to use this relationship between S, T, and M, and in particular T to M mapping throughout this little talk. So now consider a cloud of mixed particles. Let's imagine that our cloud contains particles in their original position, and for every one in its original position, there's one in its reciprocal position, meaning that to them it looks like the reciprocal geometry, a kind of symmetry. In this way, when we do the reciprocity, when we change transmitter and receiver, the system will look the same. It looks invariant. Nothing has changed. It becomes a symmetry operation. Now, for that to be the case, what we have to do is we take the overall Muller matrix as the sum of the reference Muller matrix plus its reciprocal form. So we add M and MR. And when we do that, we get something like this. You can see that this matrix again, that we have some real diagonal elements. We have symmetry in some of the elements, 1, 2, and 1, 4, for example. Rather frustratingly, we have anti-symmetry. 2, 3 is minus 2, 3 in this one. So we have certainly lost some information here, because in a general Muller matrix, of course, this matrix element here don't have to be the same, but now they are forced to be the same. Even more confusing if we remember the special case of backscatter, where we had to lose a channel altogether. Well, that loss is not apparent here until you look at a particular sum of the diagonal elements here. So if you take M11 minus M22 plus M33 minus M44, that will always be 0 in backscatter systems which have reciprocity symmetry. A loss of information, a sum of things equaling 0. But this is a bit of a mess. Some symmetry, some anti-symmetry, some hidden equations inside M. Let's do the same thing now for T. Now for T, we've got T plus TR again. We just add together the reference one plus the reciprocal one for each particle. And in this case, remember we didn't have a transpose. So when we add them together, we get a complex number minus that complex number. It just becomes 0. So we get 0 here and along here, not in the diagonal element itself, but on these off diagonal elements, we do get 0. For backscatter now, it's a very simple result. As all we had, remember, we get complete 0. So T33 itself is 0. There's nothing in this channel at all. So there's nothing in this diagonal element, and there's nothing in the cross elements with all the other terms itself. Remember, we saw that for backscatter, we essentially just lose that whole information. But in the general case, we don't lose all information. This remains. This point, this number, T33, is an addition which we don't get in backscatter, but we still get zeros here, here, and here. We certainly have lost information. And a mathematical way of expressing these zeros here and here is that we have fixed an eigenvector of t. You can see that if we multiply t by this vector 0, 0, 1, 0, it remains unchanged. We just get t33 times 0, 0, 1, 0. So this is an eigenvector of t. And this is an important general result, that symmetry impacts on the eigenvectors of this matrix T, which it does not so clearly with M. It's not such a simple interpretation. So the moral is, if you want to study symmetry and its consequences, use the coherency matrix, the T formulation, rather than M. So interesting, we've lost information. That information loss can be represented by fixing an eigenvector. So even before we make the measurement, we know what an eigenvector of t is going to be. In other words, we know that these elements are going to be 0 here, and we've lost these 3 complex numbers that used to be here. Information loss. So that's one example. We've worked that one through in quite some detail, but is that the only way we can lose information? Just reciprocity? Well, no. There are other ways, and thankfully we can tie them all together in a general approach. So let's call this the scattering matrix group, and it's how many ways do we have to lose information. Remember, we have this master problem here with light coming in from A, and we are detecting the light coming out in B, and we have a scattering matrix for this problem which has got 4 complex numbers. Just call them A, B, C, and D here. And we saw in the previous case how we can generate another problem by exchanging transmitter and receiver, but we can do other things. We can not only rotate the problem by 180 degrees about the bisectrix, which is what we did before, but we can mirror the problem with respect to the scattering plane itself, or we can mirror the original problem with respect to the bisectrix plane. So there are mirror reflections we can do. These are symmetry operations. Let's call them alpha, beta, and gamma. And this was all worked out, first of all, in this wonderful little book by van der Hulst on light scattering by small particles. And it means that when it comes to considering a general symmetry case, we've only got 3 daughters from one parent to worry about. The A, B, C, D goes to A minus C minus B, D, which is just reciprocity. But you can see these other ones are slightly different. This one, for example, gamma, the A and D, but C and B this time just change over. There's just a transpose here. But these are all the operations that we have to consider. So now you can see that to answer the question about what is the most severe symmetry operations that we can imagine, we just need to add up the Muller matrices or coherency matrices for all of these and see what the eigenvectors of T tell us. So it's quite a simple procedure. Let's do it. So here's the full symmetry. There's the master, now expressed in terms of a Pauli vector K rather than a scattering matrix, just sums and differences of the elements stacked into a vector. And these are the daughter ones. There's three of them, the reciprocity one, and then the other two, beta and gamma, as shown here. And now we imagine a cloud of these particles, and for every particle in this position, we've got particles in the other three as well. So we have kind of random orientations of these particles in some kind of complex random environment. Well, when you do that, you add up all of the coherency matrices for this. This is what you get. And you can see that you get nearly a diagonal system. You get the diagonal elements here, lots more zeros here now, but one non-zero off diagonal element. One complex number survives all of this. And this was indeed what Chandrasekhar found in his studies of atmospheres. And if you put that now into the Muller matrix form, you can just convert it. It comes to a well-known form, block diagonal Muller matrix. So you get these two blocks here are zero, and there's a symmetry here, an anti-symmetry in this element here. So this is a well-known form of the Muller matrix for scattering by random ensembles. But this coherency matrix form is the key thing, because again, it's the eigenvectors. We can see that yes, reciprocity, remember, fixes one eigenvalue as 0, 0, 1, 0, but we've got another one fixed, 0, 0, 0, 1 now. So we've fixed two of the eigenvectors, but not in this little space here. We have a little two-dimensional problem up here that is allowed to rotate, just like the circle was allowed to rotate. We can rotate these elements amongst each other in a consistent manner and still not violate the symmetry. It still embeds the symmetry. And that's a key thing here. That's where the information survives. So formally we can find what the eigenvalues of this are. As we've seen, 3 and 4 are just the elements themselves here, but this is a little 2 by 2 matrix, and we know how to find the eigenvalues of a 2 by 2 matrix. But key for us is the unitary matrix, the eigenvectors stacked together here, which transform these eigenvalues. Remember, 2 of them are fixed, but 1 of them isn't. We've got a parameter here, alpha, and we've got a phase shift phi. And this alpha appears like cosines and sines. It looks a bit like a rotation. This is not a rotation in real space. It's a rotation of this parameter space, but you can think of it like a rotation of the sphere of the circle that we introduced at the beginning. So in consequence, if you have the fullest symmetry in a system that you can imagine, it destroys lots of channels, lots of zeros appear here, one complex number remains, and that gives us a rotation through what's called an alpha angle, which we're going to see contains quite a lot of important information about the residual structure in the problem as we look at some particular examples. So I promised you noise, not just information destruction. Let's see where the noise comes in. The noise comes in when we throw this solution here, so the eigenvalues and eigenvector solution of T, into the Muller matrix domain. So let's do that. So when we map this into M, T to M, for this maximally symmetric scattering system, we get this. So this is the Muller matrix in terms of the eigenvalues and that angle alpha and that phase shift phi, remember. And you see there's quite a lot of cosines and different sums and differences going on. It's a mess, the Muller matrix, but it still nonetheless can be mapped from T. Now the key thing about this is it can be written in a factored form, the sum of two components. So we can write it, the M, as a coherent part. This is a kind of polarized part, which has got an amplitude of lambda 1 minus lambda 2, the difference of the first eigenvalues, and whose polarized part, if you like, just depends on this angle alpha and the phase shift phi. That's all it depends on. This, in fact, we consider the signal, and this signal is a Muller-Jones matrix. So we can go from an M in this case to an S. So this corresponds to a simple scattering matrix, diagonal scattering matrix, which is got zeros on the off diagonal and two complex numbers on the diagonal, which we are going to give this notation, capital Z alpha phi plus and Z alpha phi minus. The plus and minus dictates whether we add or subtract cos alpha and sine alpha in this form here. And these functions we're going to call Z alpha phi, or just ZAP functions for short. And we'll see that these zap functions, these set of diagonal scattering matrices, are important in the symmetry that we're going to discuss. But the second component we get here is a diagonal Muller matrix whose elements depend just on the eigenvalues of T itself. And this is our noise. This is the depolarization. This does not have an equivalent Jones matrix. This is not a Muller-Jones matrix. This is the depolarization part of it, the noise that I was promising you. So we consider that symmetry is equal to a zap polarizer, this first element here, plus a diagonal depolarizer. Well, intriguing that we get this simple form coming from the Muller matrix through zap functions, and these things look a bit like complex numbers, right? Complex numbers are cos theta plus I sine theta. They're a little bit like complex numbers in the Euler form of complex number representation. And let's look a little bit closer at the information in zap functions. So let's talk a little bit about zap functions and what they are. And to motivate them, let's start by considering a more familiar thing, the complex number, usually given a symbol small z, and we can write it as cos theta plus I sine theta here, and its partner, which we call the conjugate, the complex conjugate, is the same, but just with a minus sign in front of I, the square root of minus 1 here. Now, this is a familiar form in terms of complex numbers, but zap functions are just a generalization of that. So we keep the plus and minus signs, but we allow the phase not to be just 90 degrees, pi by 2, which gives I or minus I, but we allow it to be anything, e to the I phi. So we've got an extra parameter here, alpha and phi, and we keep that a plus or minus. Now, one useful thing about these is they're kind of normalized in the sense that we can, just as with complex numbers, we can arrange that the sum of the squares of z and its partner is equal to 1. We can do the same with the zap functions. So they represent a kind of, they go together as a pair, and we can normalize them to be equal to 1, and that means we can scale them to any amplitude we like, or we can think about scattering without amplitude involved, and just in terms of the polarization, if you like, in terms of these zap functions. So they come as a pair, and a great way to use them as a pair is to represent the family of diagonal S matrices as shown here. So we consider this family, which we've seen is important. It's important in two ways. First of all, it's important, as we have seen, in symmetry constraints on the scattering, but also it's just inherently important for some canonical problems. We're going to show one in a moment. For example, Fresnel scattering from a surface, in-plane scattering, and Mie scattering by spheres. So we're going to have a look at that and see what information is in these zap functions here. Now, just to point out that we can always isolate the terms alpha and phi by sum and differencing these zap functions. So sum and differencing, remember, of complex numbers is the Pauli vector exponential. So the Pauli vectors, the thing that we use for t and everything, is the perfect way to access the information that's in a zap function. So let's have a look at an example of Mie scattering. So one of the great building blocks of electromagnetic scattering theory, even in its modern guise, is Mie's famous series solution for scattering by a sphere of arbitrary size and arbitrary material for all polarizations and through arbitrary scattering angles. It's a really wonderful core piece of analysis that's used again and again in applications. First published by Gustav Mie in 1908, so of a good vintage now, but still very relevant. And now, thanks to computer technology, available to all. It's very easy to calculate the series now. Now, for all the complexity of the series itself, depending on the properties of the sphere, its size, and what it's made of, and all the different functions that are needed to evaluate the scattering, what it comes down to, because of the symmetry of a sphere, is it becomes a diagonal S matrix through any scattering angle and through at any wavelength for any type of sphere, and that means it's perfect for us to represent it by zap functions. And let's have a look and see what Mie scattering looks like from a point of view of alpha and phi. So let's consider, well, an exotic sphere, why not? Let's choose diamonds. A diamond sphere, relatively small, and they have a dielectric constant epsilon r equal to 4. So these two-dimensional plots, this one here shows the scattering angle, so from 0 to 180 degrees. So this is the angle width of the A and B points, if you like, in our canonical problem. So 0 degrees is forward scatter, straight ahead, and 180 degrees is back scatter, that special case that we were considering. So that's what's along this axis. Up here is the size of the sphere. So this is a very small sphere, a size parameter of 0.1, and we're going up to a size parameter of 0.4 to show what happens. And we're showing the two parameters alpha and phi. Let's consider alpha first of all. And we see that it varies across its full range. The color code here is from 0 degrees in the forward direction through 90 degrees in the backscatter direction. And it goes through 45 degrees roughly in the middle. And in fact, for small particles, you can see that alpha is pretty much just the scattering angle divided by 2. And it changes slowly as we come up in the particle size. And what happens is that the upper half of the alpha variation from 45 up to 90 gets squeezed into a cone, a narrower cone in the backscatter direction. So alpha has got something to do with scattering angle, and it varies quite smoothly and predictably with particle size. Phi, well, actually, it's particularly for low values, it's pretty boring. It doesn't do much, and that's a pretty good thing, actually. And that's got to do, we'll see later on, with the fact that we're considering a pure diamond, if you like, with a real dielectric constant. There's no imaginary part. There's no losses in this sphere. And for lossless spheres, this phase is pretty benign. It just sits at a value, and it does vary eventually. It does start to vary as you go up in particle size, but for quite a range of particle sizes, for small particles, it's quite interestingly boring in a way. So that's of course a me series, a hypothetical situation in many ways. What do we do when we have to consider the real world? And to do that, well, we have to consider non-spherical particles. So, little introduction to the particle zoo. The prevalence of non-spherical particles in all kinds of domains. Spheres can be found, but also cubes and aggregates of particles sticking together, little cylinders and disks and all kinds of aggregates and so on. So we have to consider not just spheres for all particle sizes. We have to take into account these. But these things are a little bit like the detail of the birds in that introduction that I gave you. They are beautiful in their way and extremely complex, some of them, to describe geometrically. But if you're putting them together and shaking them up in a tin and making a cloud out of them, then symmetry takes care of it and it smooths out lots of the variations. But anyway, as a step towards this full complexity, even me himself said that at the end of his famous 1908 paper, that for the sake of completeness, it's absolutely necessary to investigate the behavior of ellipsoidal particles. So these are like cigar-shaped or disc-shaped particles as a next step from spherical into non-spherical. And there's a very nice way of dealing with those now, which we're going to have a look at. So meet Smarties. Smarties is an example of a full Maxwell solver. In other words, it solves Maxwell's equations completely for ellipsoids, both prolate, so cigar type shaped, and oblate, kind of Smartie shaped. In fact, that's where the word Smarties comes from. It's a shape of a small candy that's available. And this, there's details in this reference here, how to download this software and run it, and it allows you to run exactly the same as the me series in a way. We can find out the solution for the ellipsoids. Now, of course, in this case, the scattering matrix for a particular ellipsoid in a particular orientation is not diagonal. But if we put together a cloud of them, then they will be. And this code, in fact, allows you to calculate the response of a cloud of ellipsoids in random orientations, which is exactly what we're seeing. So let's have a look at that. So let's imagine a cloud of diamond ellipsoids, so the same dielectric constant as before. And what we're showing here, again, are the 16 elements of the Muller matrix, all normalized to the 1 element, so the power is taken out of it. And along here, again, scattering angle on each little graph here from 0, which is forward scattering, to 180 degrees, which is back scatter. And we can see a familiar structure. There are zeros here and here. This is a block diagonal matrix, and you'll see there's an anti-symmetry there and a symmetry between those elements. So this is exactly the structure of symmetry that we mentioned a few slides ago. So despite the fact that we've got a cloud of non-spherical particles, quite complicated things, what we end up with is a zap function plus the depolarized noise, of course. So let's have a look at a real example now, going ultimately now to full complexity, and let's find one of the most complex particles we can. This is an example taken from the Amsterdam Granada light scattering database, which is a wonderful facility with measurements on lots and lots of particles and images of the particles themselves. This is a piece of volcanic ash. You can see it may have some kind of ellipsoidal structure, but you can see it's a very complicated particle itself, and when you put lots of these together, again, it doesn't matter what the individual complicated responses of this particle, what you get is a smoothed out block diagonal Muller matrix and just a zap function. So these two graphs here represent all there is to extract what survives symmetry of the cloud. And you can see here's alpha again, it's starting from 0 and going up to nearly 90 degrees. And you can see that it's the 45 degree point is happening around 130 degrees scattering angle. So we've got a kind of a cone of compression of the alpha angle variation in the second half, which remember is an indicator of particle size really. And the phase, again, well, it's pretty boring for large elements of scattering. It's pretty constant. It is not now 0 or 180 degrees. You see it sits around about 100 degrees or so. There's some structure close to backscatter and close to forward scatter, but for large regions of scattering, it's pretty constant, and it's an indicator, in fact, that these particles are not lossless. They're not diamonds, of course. They are complex structural materials, often with losses, so they have an imaginary part of the dielectric constant. So all this illustrates that symmetry causes us to lose information. We lose all the wonderful information that's about this particle, but something does survive, some parameters survive, and the symmetry model tells us what parameters, how to extract them in terms of alpha and phi, the zap function. So let's go back now and consider radar or consider backscatter and have a look at how all this stuff maps into the radar world. So let's go back to backscatter to consider the case, remember, where A and B, the 2 points at either end of our wave propagation direction, coincide at the same spot. Now this is a rather special case, of course, of the general case that we've considered so far, but it's a very important example because of its domination in radar. Radar is nearly always a monostatic system, and that can be illustrated with respect to this satellite here. This is ALOS-2, operated by the Japanese space agency JAXA, and as well as seeing these large solar arrays here for powering the satellite, you see this is the radar antenna here, and it acts both to transmit and receive signals from the Earth's surface and build up global data sets of backscatter polarimetry. Now, if you've been paying attention during this talk, you'll realize, of course, that immediately, convenient as this manufacturing technique may be for radars, we immediately lose information through reciprocity symmetry because we've lost a whole channel of data, and that's manifest usually in radar by saying that the scattering matrix is symmetric. Now, if you look back in our notes, you'll see that it was anti-symmetric in the off-diagonal elements. That's because radar uses a slightly different coordinate system called BSA, backscatter alignment, but it's the same idea. In this case, the difference of the off-diagonal channels is going to be 0. And so our Pauli vector loses a complete channel, normally just not mentioned even in the radar literature, of course. They normally just start with a 3-dimensional, not realizing in fact that there is a 4-dimensional space of possibilities out there. And of course T, as we've mentioned already, then becomes a 3x3 matrix. So let's have a look a bit more closely at the implications for this backscatter case for our symmetry models, and we're going to also take a little a comparison between our approach using zap functions plus a depolarizer compared to what is actually commonly used in the radar literature now, and take a little bit of a critical view of that. So let's go. So, backscatter and symmetry, how does it work? Well, a key element for backscatter systems is that rotation of the satellite, rotation of the antenna, is equivalent to rotation of the pixel on the ground. So vice versa, if there's something that rotates something on the ground, it'll be seen as a mismatch in the rotation of our reference antenna system. And that's an important idea, and it tends to underpin everything that's done in radar scattering modeling. And let's motivate that by considering a following kind of general model. Let's imagine that we have a parent particle, a scattering mechanism as it's called. It's going to be a zap function. Now the zap function, remember, has two parameters, alpha and phi, and here it is in its rank 1 T-matrix form. And you can consider it to be, for example, an ellipsoid particle aligned with the radar coordinates, its vertical axis aligned with those, in which case we would get a zap function like this. We'll see later, however, that this is not this is just an example. There's a wide range of variations of types of mechanism that we can model using this zap function. So we don't see just a single particle, of course, in a radar backscatter signal. We tend to average over spatially over using speckle filters and so on. And so we end up with a kind of an ensemble, a mixture of things. And it's the symmetry properties of that mixture that dominates. So how do we cope with that? Well, we cope with it by saying that, well, we've still got the same particle, but we just see it in different orientations. For example, this might be branches in a canopy of a forest, for example. They have a distribution of orientation theta. And so what we have to do is consider not just a rotated version of this matrix, which we can do with a rotation matrix R as shown here, but we also have to integrate, we have to average over a distribution, and P of theta here is some probability distribution. It might be uniform, might be Gaussian, whatever, but in principle it's a distribution of angles, and we're going to add over those distributions. And when you do that, you get this form here for the observed matrix. Now this is a mixture of a zap function and depolarizes, just as we got used to in the optical case. X, Y, and Z, these parameters here, X, Y, and Z, they are from the underlying rank 1 parent. That is the alpha angle, if you like, and the phi angle of the polarized part. The depolarization is caused by this integration, and that's got two parameters, tau and chi. And here they are. And here they're defined. So they're moments of the distribution against cos 2 theta. So tau, because cos theta can be positive or negative, this tau can be 0. But chi is always positive because it's a cos squared 2 theta against p of theta. So these two important parameters here we'll see dictate the level of depolarization noise that we have on top of our zap function. So it's exactly the same kind of language that we used before. Now, we started off by assuming that we were aligned with the reference particle here in the coordinates, but maybe our radar might be misaligned with this. In other words, the particle itself might have some mean orientation in its distribution, and that may be different to the reference that we're using in the radar system. And so we have to allow for the idea that there's a mean offset in rotation, which we can do just by rotating this model, this depolarizer model, through an angle theta. And when we do that, we've now got the flexibility to allow for mismatch between radar and target. So this model, fairly straightforward, it just imagines rank 1 systems distributed with some probability in a plane, normal to the radar line of sight, and we get a particular structure in this matrix. And this structure here is used to explain, I think, 99% of all radar modeling for backscatter systems. So let's take a look at the implications of this model. And one implication, in fact, is we can simplify it even further, and it often is simplified because even all these parameters, the x, y, z's, and taus and chi's, are too much for many radar applications. And so there is a desire to find a simplified version of it, and that extreme simplified version is when we insist not only do we have rotations, but that this matrix remains invariant to any such rotations, so that we don't have any orientation effects at all in the distribution. That's called azimuthal symmetry, and let's go and take a look. So here's the strongest form of symmetry used in radar, where we insist that rotation invariance in backscatter. That is, when we operate on this depolarizer zap combination with a rotation matrix, it doesn't change. Right, just like our circle doesn't change when we rotate it. So we insist on that. And the only way we can satisfy this constraint is that the depolarizer must now be diagonal like this. Not only is it diagonal, so we've lost all information about the phase, then these two elements must be the same as well. So it's only got 2 degrees of freedom, T11 and T22. And you can see, if you look back, this is a special case of a reflection symmetry case that we considered in the previous slide, when you set chi to 0.5 and tau, phi, and alpha all equal to 0. So they're all fixed by this assumption of symmetry. Now, it's interesting to see the noise decomposition representation of this, because this is just like the general case, represents a zap function plus noise. So let's take a look at that. So first of all, in the T-matrix form, what we get is we get a polarized part, which is always of this form, with a 1 in the first element and zeros everywhere else, and its amplitude is given by the difference T11 minus T22 in this diagonal matrix here. So the signal always has the same form, 1 here and zeros everywhere else, which means it has an underlying scattering matrix. It's rank 1, so we can go back up that scattering triangle to S, and S is just 1, 0, 0, 1. It's a mirror. So it's always a mirror when we insist on rotation invariance, the signal. There is a noise part, and that noise part has got an amplitude of T22, and it's got equal eigenvalues here, 1, 1, 1 along the diagonal, and zeros elsewhere. Now, sometimes people think this is noise, this is random noise, it has no structure, but remember, there is in fact a 0 eigenvalue tucked away here due to reciprocity. So actually we should be considering this to be 1, 1, 1 and a 0. And that means that we have some structure even to the noise. And to see that, we can go to the Muller matrix form of this decomposition. So here's the Muller matrix form. So here's the mirror signal. This is a Muller-Jones matrix for a mirror. And the noise part, it's not a perfect depolarizer. A perfect depolarizer in M terms would be something here and 0 everywhere else. You see that it's a partial depolarizer. It generates a partially polarized wave with a degree of polarization of 1/3, a 33% polarizer. So that's rather surprising to some because of this looks like noise, but it's actually a kind of a colored noise. But this is all there is if we have azimuthal symmetry. Now, why do we do this? Well, this is a common assumption made in radar because of parsimony. In radar problems, often people want to minimize the number of parameters they need to estimate from data. So people often make this assumption of azimuthal symmetry in advance and force this model onto the data. And that's one of the things that I'm going to take issue with as we go forward. So let's now have a look and see what happens when we relax this azimuthal symmetry and go back to reflection symmetry. Remember, there we had alpha could be anything, right? It's full range. There was no restriction on that alpha in the zap function. And let's allow that again in radar backscatter, and let's have a look at the full spectrum of alpha values and what they mean in backscatter. So this graphic is supposed to illustrate the utility of the full alpha range, the full alpha spectrum that we were talking about earlier. In the previous slide, we considered the case of azimuthal symmetry, and there we showed that alpha is always equal to 0, which in backscatter means it has the symmetry of a sphere or a mirror. But natural terrain does not reflect like a mirror. We have a lot of variations of natural terrain. That's what this graphic is supposed to illustrate. We've got forests and croplands and grasslands and urban areas and so on. And it's for these more general situations that we can make use of the full variation of alpha from 0 to 90 degrees, which is the alpha spectrum. Now, all this complexity here can be mapped into a simple idea based on our reflection symmetric model as shown here. So we start with alpha equals 0, where we have a mirror, and surfaces like water surfaces at normal incidence do look like specular reflections like a mirror. But if you come away from that, then alpha starts to increase, and we get to a situation where we have different reflections and different polarizations. And you can imagine it from an equivalent ellipsoidal particle like this. And as these ellipsoidal particle gets more and more oblate, we get less and less of one reflection and more of another. We end up with a dipole, which just has one polarization response. And that's the full variation of alpha equals 0 to 45 degrees in a smooth transition along this part of the curve. Now, that's exactly how surfaces behave. If we come a water surface, for example, away from normal incidence, then we get this kind of behavior where we get differences in the reflection coefficient due to boundary conditions on the water surface itself. So that allows us to deal with more interesting situations of surface scattering. Now, beyond 45 degrees, of course, as a smooth transition into this region, we start to be able to consider reflection from concave structures, things which are like a boomerang shape here, not actual boomerangs, but just something to imagine where you can get reflection, internal reflection between two surfaces and coming back to you. So this multiple scattering effect is what dominates from alpha 45 degrees all the way up to 90 degrees. And this can happen in natural terrain with reflections from the ground and the trunk, which gives us a kind of reflection like that, even from the ground, the surface onto stems of plants. And of course, especially when we come to think about buildings, we get strong right angles in structures, and we get almost exactly the same as this geometry. All the way to 90 degrees. 90 degrees represents an extreme value where we have two metallic surfaces and a man-made structure, and that would be the extreme value of alpha. So this full range of alpha, the alpha spectrum, is very important for mapping into different types of land surface. And of course, in remote sensing, we do the opposite. We look at a land surface and interpret different parts of it from where they are on this alpha spectrum. Now this is the alpha angle is part of the ZAP function, the polarized part. Where does the noise come from? Well, remember, in our model, the noise comes from uncertainty, essentially, about the orientation of these objects here. So if they have some distribution of rotation, like a particle here, then we can get rotation of this particle in different orientations, depending on what its probability distribution is. Then we get an uncertainty, we get a noise contribution to the signal. And that's true for these kind of irregular particles here, of course, but also for these concave structures, these dihedral effects. They too have the same depolarization noise. If you look straight into the face of this dihedral here, this is what you get, and it can have some distribution of angle. So those two depolarization parameters, tau and chi, you can think of as just mapping into uncertainty about the orientation of the structures that we're looking at. And that, of course, in itself is some kind of information. For example, in an urban area, the orientation of these buildings is quite fixed, whereas if we imagine a forest canopy, there will be more uncertainty. So we will expect some difference in the depolarization noise in these two scenarios. So this is what you get when you relax the whole idea of azimuthal symmetry and you consider instead reflection symmetry. But even so, this model is still quite simple. It imagines a distribution of objects, all the same object rotated in a plane, and depolarization caused by rotation only. And nature, of course, real world complexity is much more complicated than that. And so we need a way of assessing, even with this remote sensing, with this reflection symmetric model, how good the model fit is to any observed T matrix, any observed scattering from the ground surface. And that's what we're going to focus on now, just how good is this alpha model, this ZAP plus depolarizer model at dealing with real nature, with real targets. And that's where we are going next. So how do we measure how good our model assumption is? Well, thankfully there is a machinery for helping us, and that's the process of what's called rank reduction. And this is how it works. So we have a sample matrix T, and we say that that's going to be equal to the sum of two components. Our model, which is a reflection symmetric model with some coefficient, and a remainder, which does not fit our model. Let's call it unsymmetric, with a coefficient MR. And how do we find MS? We want that to be, of course, as much bigger than MR for our model to be a good fit. So, well, we do this by turning this equation around so that MS TRS is a subtraction of T minus the unsymmetric part. And the key is that the unsymmetric part must still be a physical Muller matrix. It must still be a positive semi-definite coherency matrix. And for that to be the constraint, it means that we have to reduce its rank of the remainder, hence rank reduction. That means that one of its eigenvalues goes to 0. If we increase MS beyond that, then we'll end up with a negative eigenvalue and a non-physical result. That's the essence of it. And the way you do it is you just, for a fixed set of model parameters, you just find the minimum eigenvalue of the inverse of your model times the sample. We want to find the best fit of the model, so we repeat that process over all the parameters of the model itself, and we choose the best fit from the maximum of the minimum eigenvalues. So that's the procedure. So all we need is a model, and we have one, as we derived in the previous slide. So we have our ZAP plus depolarizer, sandwiched between a mean rotation to allow the fact that we may have a misalignment between our radar antenna and the ground. And the whole thing is given by this. It's 5 parameters: alpha, phi, tau, and chi, and of course theta in here. So it's a 5-dimensional search that we need to do. Now, to help us with this multidimensional search, we can actually make some assumptions. We can find the fixed ZAP function because it is invariant to rotation, so there will be no rotation effect on alpha, which we can just get from the cosine of the square root of the first element here, and phi, which is the phase of this second element, the T12 element. So we can fix those. We don't need to search for them. That is essentially our ZAP function. Nice and easy. But then we need to find the tau and chi parameters in amongst the rest of the matrix. And to do that, we need a 3-dimensional depolarizer search with theta, tau, and chi. And we can do this by any optimization technique you like, but we can set up initial estimates quite simply by assuming that if T is actually fully fitting already to our model, so that MS is equal to 1. If that's the case, then we can get initial estimates chi naught and tau naught just from the elements of our sample matrix T itself. But then we put them in an optimizer and we iterate around this procedure to then maximize the minimum eigenvalue across all the 3 parameters, theta, tau, and chi. And in this way, we get a solution, the best fit, and also we know how well it fits by looking at MS. Now we're going to assume everything's trace normalized so that MS plus MR is equal to 1. And that gives us an easy, so we don't have to worry about absolute amplitudes, just relative amplitudes between the 2 components. So let's have a look at an example. So this is an example to illustrate the previous procedure, and we're going to use data from the ILOS-2, the JAXA satellite that we talked about earlier at a wavelength of 30 centimeters. And the test site we're going to use is a patch of forest in Canada. It's a test forest shown here in green, which allows us, this mask allows us to extract all the pixels from the ALOS data, which are just forest cover indeed, and then we can average them all up. So there's many thousands of pixels inside this mask area here, and we're going to just average them all just to give an indication of the type of result that you get. And when you average them all up, you get a Muller matrix that looks like this. And what we're going to do now is see how much of this can be fitted by this model, this ZAP plus depolarizer model based on rotation noise only. And the first thing we do is we convert M into a T, and then from T we can immediately get 2 of the parameters, the alpha angle and the phi, and you can see that alpha is close to 45 degrees, so it's a kind of dipole-like scattering here, and the phi angle is definitely not 0, even though averaged over an extensive forest region, it still comes in at around 30 degrees or so, and that's quite important, as we'll see. So those 2 are fixed, but what about the depolarizers? Well, Remember, in the previous slide, we said we have to do a search. Well, here's the results of that search. So this is the tau chi plane between 0 and 1 and 0 and 1 for each of them. And each point here, what we're showing is the minimum eigenvalue of the product between our model and the data sample itself, t. And you see it varies. Notice incidentally we get a quadratic curve here, and that's because chi must be greater than or equal to tau squared. And why is that? Well, that's just so that we don't get a negative eigenvalue for the remainder matrix again. So this region here is the valid region. And you can see that we have a clear peak. So this is the max of the min process. And well, you maybe can't see, but the little red star is the peak itself, and the black cross is where we started. So this model is almost fitting straight away to the reflection symmetric model, and in fact this peak here is over 98% in terms of its fit to the actual data itself. Now, interestingly enough, this point here, this maximum point, doesn't sit anywhere near the azimuth symmetry point. This is not an azimuthally symmetric canopy that we're seeing here. What we're seeing is some structure in the canopy. You can see that chi is about 0.6 and tau is about 0.18. And so there is some noise caused by rotation variation in the canopy itself, but it's not completely random, and the assumption of azimuthal symmetry would not be justified even for such an extensive average as this particular structure here. Theta comes in essentially as 0, as we would expect, no strong orientation effects on this particular canopy itself. So that gives an example and illustrates how we can use the model to extract the key parameters of the model itself, the zap function plus the two depolarizing coefficients, and we can also measure how well this model fits against the data itself, and that's quite a nice set of procedures to have. So let's just move on and summarize that. So here are the physical parameters from backscatter symmetry assumptions. Again, the presence of symmetry in the backscatter direction does destroy parameters. It removes channels, as the reciprocity theorem does as well. But there is some residual, and that residual is got a T matrix like this. There is one complex number which survives it, and that can be parameterized, as we have shown, by zap functions x, y, and z, and two parameters tau and chi. So we have 4 key parameters coming out of this, in addition to the backscatter, the amplitude that we see, and also this mean orientation, this shift between the sensor rotation and the pixel itself. So 4 key physical parameters, and key amongst them is alpha, this alpha angle, which can range across its full spectrum from 0 to 90 degrees. And the example we showed just now was 45, but we have this full spectrum available, 0 for spheres or mirror type reflections, 45 for dipoles, but also further on into dihedrals and these concave kind structures. So it gives us a great deal of flexibility in extracting information about different types of land use. The alpha parameter is well known in radar polarimetry. It's used already quite extensively for classification of different land uses types. But a bit more controversially is the phase itself here, which is seldom used, and we can see that it clearly does come out of the symmetry arguments as it did in the general case. This is called the Pauli phase because it's the phase of between the first 2 Pauli channels in the Pauli vector, and it's related, as we have seen earlier, to the dielectric constant, particularly the imaginary part, but also to structure in the volume itself, whether it's predominantly horizontal or vertical in its scattering. And this phase survives symmetry averaging, and at the moment, suffice to say, this is not really widely used in modeling. We'll have a look at that in a moment. So that's the polarized part of the signal that we get in backscatter, an alpha and a phi, the zap function. Now, we get then 2 depolarization parameters. These reflect our uncertainty about the orientation aspect of this particular zap function, and we've got chi and tau, and they represent basically the amount of incoherent cross-polarization generation that we get, and also essentially the coherence of this phase, this Pauli phase that we get. If there's more and more noise on the signal, then the phase, the coherence will reduce, and eventually, of course, we'll end up with an azimuthally symmetric case, and no phase information at all. So all of this seems quite straightforward, and we have a way not just of interpreting these, but as I say, of having a look at how well this fits the data, this model fits the data. So let's finish off by having a wee look at the people's choice. This is not the way that most people would model backscatter in radar, and so we're going to have a look at the models that are more widely used and compare them against this version. So the people's choice. Well, there are basically three classes that we can talk about. In the first one, the simplest one, was full azimuthal symmetry. And of course here this really has zero polyphase. So we assume a diagonal coherency matrix. And further remember that these two elements, T22 and T33, are equal. And this is what we get when P of theta, the distribution, is actually a uniform distribution. So all possible angles the particles are forming. It really is a random cloud, in which case tau, the integral over cos 2 theta, becomes 0, and chi, which is this thing, becomes equal to a half. And we end up with this situation, and for dipoles we then get this well-known structure of a half, a quarter, quarter. So we get a 2-to-1 ratio between the biggest eigenvalue and the second. This was one of the first models used to describe random structures and is part of the Freeman-Durden or Freeman decomposition, which is still widely used in radar. More recently, people have considered other diagonal versions of this, and one of the most common ones is to assume that the 1/3, 1/3, 1/3. So we just have what looks like noise. So remember this equal eigenvalues. Remember, it's not noise. In fact, it can be constructed very specifically from some of these concave dihedral, a random cloud of those with an alpha of 55 degrees. When you do the integration, you'll then get this type of response here. So this is used because it's like a kind of a noise source, and this one is a dipole cloud, a random dipole cloud, and these still are very useful, but no phase information. And you've really got to test whether these are appropriate for the data sets you're getting. In terms of the previous one we saw in that forest, that this assumption of a diagonal T matrix is not really supported. So this idea that perhaps there might be orientation effects involved is a second class of popular choices, and in which case it's usual to assume some kind of probability distribution. And one of the most common ones is a cos theta one, and that then just gives us one free parameter, and we assume again that alpha equals 45 degrees, so that means a dipole cloud, but still no phase in this one. And in this case, if you have a cosine distribution, you do these integrals. Tau is then 1/3, and chi is 7/15, almost a half. And you see then that this is the structure that you get for the coherency matrix of the volume. And this is either for H dominant or V dominant, and you can see the phase at the tau here flips sign when we have H or V being the dominant case. And these two cases here are part of what's called the Yamaguchi decomposition. It's a kind of extension of Freeman to consider more variety in terms of the type of random volume or symmetric volume that we are dealing with. But again, aside from the plus or minus sign here, no consideration of phase, no polyphase due to the scattering from the random volume itself. Now, a third class, which is called GVSM, stands for Generalized Volume Scattering Model, is really a great example of how parsimony rules in radar. It's a more elaborate, it's a kind of continuous version of this Yamaguchi, in fact, but it just allows one free parameter, and that one free parameter here is called gamma. It's the ratio of scattering of HH and VV, so the horizontal over vertical ratio. And from that one parameter, you can fill a matrix then, which is a positive semi-definite matrix. It's a fully valid matrix, and the X, Y's, and Z, the components for that matrix, can be just referred to one parameter, gamma, here. And then you extract this full information from T. Again, although it's called generalized, it's not really that generalized because there is no phase in Z here. Z is just gamma -1 and gamma is real. So it has no phase information particularly inside it any more than the Yamaguchi does. So All of these are used in various ways in the radar community, but you can see that none of them really make use of the full information in terms of the parallel phase and the alpha angle possibilities that are there. So that brings us to the conclusions. Let's summarize where we have been. First of all, one of my main ideas here has been that we should see symmetry as a mixed property. Sometimes it can be useful for simplifying models, and particularly when parsimony is key. We want to minimize the number of parameters we need to estimate, but it acts as a destroyer of detail. So there's no point in worrying too much about detail unless you know what kind of context you're going to see that detail in, what kind of symmetry assumptions you're going to have to make. We lose information, but as we've seen, and as Chandrasekhar first pointed out, not all information gets wiped out. We have some that remains, and that remaining information we have seen often comes out as a zap function plus a depolarizing noise. Now, worse than that, symmetry does add depolarization noise. We've seen that. These variance parameters that come out, which are not to do really with physical parameters, but with our uncertainty about parameters in the signal. An important point is that this symmetry residue, extracting the noise and that, is best done in the T domain, I would suggest, even in the optics community, not the polarimetrics, and there are two good reasons for this. First of all, symmetry directly impacts the eigenvectors of T. Recall that when we talked about the idea of reciprocity symmetry and reciprocity theorem, that immediately popped out in the T domain as a fixed eigenvector, and it's not so clear to do it with M. Of course, M still has those constraints, but they're not so easy to identify. The second reason is that the positive semi-definite condition on T means that we can be exploited via Wedderburn, which is rank reduction, to develop algorithms for symmetric component extraction. So that is, we get a way of assessing how good our model is as a fit to the data by using the positive semi-definite condition and rank reduction. And we've seen examples of that in the development of some data that we just had a look at. A key idea, of course, is that the polarized residue, whatever it is, can be represented by this thing called a zap function pair. And they have two parameters, alpha and phi. Remember, you can think of them just as a kind of extended complex number. But the alpha and phi have specific physical interpretations that we've had a look at. And a key thing is they provide a common architecture for optical and radar scattering. So hopefully both domains can talk to each other in optics and radar by using this joint formulation. So we have a common language for all of scattering. We don't have to think of it as two different communities, just as one process, which is the scattering of waves. And a final little point about radar modeling, I would suggest it's not yet fully realized. There's been so much work done on modeling random media in radar backscatter, but frustratingly, I think it's still not there, and I have three particular suggestions that we've seen. First of all, the Pauli phase should be folded into volume models. It's there, it's allowed in the symmetry, it survives at the symmetry averaging that we put forward, except in its most extreme form of azimuthal symmetry. But as we've seen, that's a rather artificial mathematical structure rather than anything matching to the physics of what we see in real domains. So currently Pauli phase is missing. Put it in. The second thing is related to that, of course, be careful of assuming azimuthal symmetry. So many approaches assume that a priori for one of the components, and it's often not supported by the data. So at least you should have a look and check that in certain types of data you do have this azimuthal symmetry assumption before you embed it into your algorithm. And the final point is to do with the rotation correction, which is important. If we have reflection symmetry, we must allow for the possibility of a mismatch, and that is best employed as part of the decomposition. So we put it as a three-dimensional optimization, including rotation, and not just a two-dimensional fix. And so we can embed the rotation in this estimation, this rank reduction estimation idea as well. So there we are. I hope now you're not so frightened about symmetry, but perhaps you do have a respect for how it plays an important role in the way that we use polarized waves to sense the environment around us.